Hello, what we're going to talk about today is modeling using similarity. Most likely I'm going to break this video up into two videos. As you go on to Edpuzzle, there will be two videos. Objective: students will be able to use properties of similar triangles to solve real-world problems. Some of the vocabulary you may hear is similar, corresponding sides, corresponding angles, congruent, proportional, parallel, side splitter theorem. And so one of the things that I just thought that would be unique is they started talking about not all flagpoles are perfectly upright. Some are oblique. So they did define each of these for you. So upright and where it comes from, and then oblique. And what does that mean? It means neither parallel nor at a right angle, but slanted. Imagine an oblique flagpole in front of an abandoned building. The question is, can we use the sunlight and shadows to determine the length of the flagpole? And right now, something that you may have seen, and some of you are going on the college tour to New York City, so I grabbed from Central Park a sundial. And sort of a sundial is used similarly, that sort of puts the angle at a very specific angle and allows the point to land right on, to kind of give you an idea of what time it is. Well, this flagpole can be used sort of similarly, but we'll just do the flagpole. It's blue, and it would cast a shadow down on the paper as such. Assume that we know the following information. The length of the shadow of the flagpole is 15 feet. And so if the length of the shadow, flagpole becomes important because it designates where it's coming from, is 15 feet. There's a mark on the flagpole 3 feet up. So they're basically saying that I've identified this spot on the flagpole. It's 3 feet up. And its shadow comes across like this. And this is 1.7 feet. Okay? And essentially what they want to figure out is, what is the length of the flagpole itself? And so as you're thinking about this, the first question you may have is, are they similar? Well, from the sun, you've got the same angle. Okay, it beads down, and the shadow from the top to the bottom comes this way and this way. Okay, so what we do know is that this angle is the same as that angle to the sun, and they share an angle. So by angle we do end up having similar triangles. And how can you use similar triangles? Basically, I can set up the proportion with the length of the flagpole itself over the length of the shadow equals the little segmented part over its known shadow. And so you can do this a couple different ways, but cross multiplication is not my favorite method. So what we're going to do is undo the division of both sides. This 1.7 simplifies with that 1.7, this 15 simplifies with this 15, and so now I have 45, which is 3 times 15 equals 1.7 times x. And of course, using your trusty calculator, 45 divided by 1.7 equals 26.47. Approximately is the value of x. And so what does this actually mean? The flagpole is approximately 26.5 feet long. Okay, we use this fairly regularly as we start problems. And it opens this up to like a whole entire unit, what we call trigonometry, but we're going to continue looking at it just in terms of the similarity between the triangles. So if you want to determine the approximate height of one of the tallest buildings in the city, there's no way you can have a tape measure that goes top to bottom, the height that you want to measure. You were told that if you place a mirror some distance from yourself so that you can see the top of the building, in the mirror, then you can indirectly measure the height using similar triangles. To me, that's kind of a neat fact, that if I put a mirror, here's where the mirror is, I can kind of figure out where the height of the building. And the question being is like, how do I know that the two triangles are similar? Well, to measure the height of the person, we look at the perpendicular distance from the ground to the top of the person's head. Okay, and so we have a perpendicular here, and we have a perpendicular to the ground, and the building should be perpendicular. And then we know this is 36 and this is 36, so by AA, triangles are similar. Okay, then they give us some information. It says, label the diagram. The person is 5.3 feet. The distance from, or to eye level, I should say, the distance from the person to the mirror. So this is eye level. It starts here. So that's 5.3. The distance from the person to the mirror is 7.2 feet. So this distance right here is 7.2 feet. All right. So 5.3, let's just color code it. That's that person. The value I'm trying to figure out is the height of the building. And then the building distance is flat on the ground is 1,750 feet. Okay. So what is the distance from the mirror to the building? Is the 1,750 feet minus the 7.2 feet, because it was from the person to the base of the building. And so again, you may or may not need to break out your trusty calculator, but that's 1742.8 feet, which equals 1742.8 feet and 8/10. And now we have all the information that we need. Do you have enough information to determine the approximate height? If yes, let's determine it. So it's the height of the person, 5.3, or at least the eye height of that person, over the shadow, 7.2 feet, equals the height of the building, which is what I want to know, versus the length of the shadow, or not even the shadow in this case, where it's where the mirror is. So that's 1,742 and 8/10 feet. In essence, you can use the method that makes you feel most comfortable, but you'll get 1,742.8 feet equals 7.2x times 5.3. So 9,236 and 84/100 equals 7 2/10, which is 1,282.8944. So approximately the building is approximately 1,282.8944 1,283 feet tall. Okay, now not always will you round up, but because of the building itself, that 1/10 of a foot, it's not a great deal. It's 1 inch over the course of the 1,283 feet. So it's really making an understanding when you can. It's the relative understanding of when you should round and when you shouldn't. Okay, thank you for your time. We'll be back with the second video shortly.